Don't know me. I'm Lucas, and I'm going to be talking about the comparative evaluation of high order methods in laser-induced plasma flows. My advisors are Dr. Prasunda Walker as well as Dr. Sonia Dick. So some of the motivations behind this research is there's a lot of uses for laser ablation. As Jason kind of talked previously before, it's a laser impacting a surface, turning into plasma. It's a very multi-scale, multi-physics problem. So I'm looking more at that plasma and laser-induced shock that happens post the laser energy deposition. Some of the applications that are included with laser ablation are laser-induced breakdown spectroscopy, as well as material processing, other plasma diagnostics. But there comes a really large numerical challenge when we're looking at these types of flows because they contain strong shocks, contact discontinuities, especially when you're looking at outside in the ambient pressure or ambient gas, or looking on this inside right here in this plume, where it's more of like a plasma high energy bubble. And there's also steep gradients that really come into it, which really give into a numerical challenge. So a lot of low order methods, they really struggle with accuracy, as well as depicting these shocks when you're looking at a CFD simulation. And they're not as stable when you're trying to, unless you're trying to force stability for accurate plume prediction. And it's critical, especially when you're looking at plasma diagnostics. So the objectives of this research was to evaluate and compare the performance and impact of high order shock capturing spatial schemes for compressible plasma flows. A lot of previous research looks into more low order methods or TBD schemes, but a lot of those TBD schemes haven't been used since the early 2000s, late 90s period, where some of these higher order methods haven't been studied as much, or a lot of the comparative studies have been done on solver classes and open foam or other low order methods. So the main spatial methods that I compared was a first order upwind method, which is a very basic, very Newton-Raphson type method. And then I also took inspiration from other high order shock capturing methods, such as weighted essentially non-oscillatory schemes and targeted essentially non-oscillatory schemes. The numbers on the backside of those indicate the order of accuracy at which they converge. So the approach to this was to create a custom CFD solver. I looked all over and I looked at OpenFOAM and different applications, and I found that building my own CFD solver would be the kind of easiest path to go to get exactly what I wanted to. So I created it in C++, and then I used the compressible Euler equations, which just simplify down to this, where you have your conservative vector over here, which is that U. So you have your rho. And then in 2D, which is where I'm looking at, you're looking at the rho U and rho V, which are the momentum in the X and Y directions respectively, as well as your total energy on the bottom. And then here with this flux vector as what we're looking for, since they're highly nonlinear, we have to look at it in this conservative and characteristic state where you have your momentum transfer for your flux, and then you have a little bit more momentum as well as your total energy here on the bottom where pressure actually takes hold. And then to actually complete these, since they are not closed under a total system, I use the ideal equation of state. Since everything in the study is around atmospheric pressure, it can be assumed to be ideal since it is under 10 bar. And using a high energy bubble and an ambient gas solution, and I'll show that in a little bit. So a little bit about high order reconstruction methods, if you're not familiar. What they use is this stencil right here. This is just a 1D interpretation. As you have all of these indices from xi 1.5, this is a finite volume method. So you're looking at the cell interfaces. So each integer is your cell center, and you're trying to find these fluxes right here, say at this dotted line. And so what these Wino and Tino methods do is they take these stencils, depending on their order of accuracy, is for the Wino and Tino, they combine them non-linearly. So they use these advanced weights that are taken on smoothness factors to see, okay, is this one more smooth? So then we'll weight it less or weight it more. Or does this cell, say this stencil in the dotted line represents a shockwave, it's a lot less smooth. So then it will take these out completely or even reduce them. And that's the main difference with Wino and Tino, is that in a Wino method, this stencil would just be really reduced. It wouldn't have as much impact on the overall simulation. So looking more at the smooth solution to help keep that contact discontinuity. Where the Tino method, if it were looking at this one, it would completely take out that stencil 100%. So you're only relying on the smooth solution, which keeps shocks preserved a lot better. So this method really allows for more accurate shock capturing, excuse me, and a lot more reduced numerical dissipation, which you'll see a lot more in the results. So the numerical experiments that I looked at was at first an accuracy verification. Since I made my own solver, I wanted to make sure that these methods that I looked at were actually converging in the right way, as well as doing the kind of a very similar laser-induced plasma flow problems as to previous studies that I've done before. And a lot of the metrics that I examined were the shock location, shock resolution, and computational runtime. Here's a little figure showing what my computational domain as well as my boundary conditions were. On the bottom, we have a wall boundary, so that means nothing is allowed to go through it. It's able to be reflected, but nothing is allowed to go through. I chose a symmetry boundary on the left side. Since the plumes are very symmetrical in nature, both in simulation and in experimental studies, it has been shown in a lot of previous works that using a symmetry boundary gets a lot of the right results. I chose the domain to be 5 millimeters with an outflow boundary on both the top and right. This is so that all the far field physics can happen, and then they won't cause numerical instabilities on the inside of what we're actually trying to look at in this area. And then I have a small little radius with a high energy bubble, which has been shown in a lot of different studies to work very well with an initial condition. One of the main choices of using an initial condition rather than actually simulating the laser depositing its energy and having that phase transformation is due to stiffness of the problem. Since there are different rates of the simulations actually changing very quickly. So say one is changing at 100 times the other rate, that would really floor the delta time to 10 to the negative 23. So it's just not as feasible with these methods or using explicit methods like these. So the first result that I looked at is the accuracy verification. All the methods converge as expected. So as you can see, the first order is right here using different grid sizes, as well as coming down. We know 3 is in this orange, we know 5 is down here in green, and Tino 5 is down here in red. And as you can see, as we're going through these different shock capturing abilities, you actually get a really reduced thing in error. Since you're looking at a smooth solution, you can even see that the Tino is a lot more it's more accurate than even the We Know 5 method. Another thing that I looked at was computational runtime. Here's something over the entirety of a simulation run. So the simulation time I looked at was 1 millisecond. So looking here, as you can see, Tino 5 up here in this orange is showing a really lot higher runtime, where We Know 5 is down here in red, and then which is lower than We Know 3, and the first order, which you can see performed the best when you're looking at computational runtime, but there are trade-offs associated with that. And then so for computational time, the observed order convergence is on the x-axis as the y-axis as the runtime in milliseconds for an average step time. So as you can see in that bottom left corner, the first order really performs well. It converges at almost exactly 1. We know 3 converges a little bit under 3, but that just has different numerical things such as round off error and different implementations used for stability. As well as the We Know 5 actually performed over 5 and had a significantly lower runtime, where Tino 5, it did almost reach that 5 order of accuracy convergence. But as you can see, it's a lot higher runtime than, say, We Know or the first one. So looking at a little bit of the shock resolution, you'll see it a little bit more here. In this first order, we have this very smooth pressure field. And so kind of what the first order does, instead of having like a really high peak and going from one state to the next, it kind of just has a nice parabolic curve that smooths over. Looking at the We Know 3, you can kind of see that really high pressure in that shock front. It kind of gets collapsed down. So as you're seeing that these are actually capturing the shocks a lot better. And looking into We Know 5 and Tino 5, you're looking at an even sharper contact discontinuity any better shock capturing methods. And even in these two, it's a little hard to see without or with all these lights. But there are other pressure gradients coming in right here in Spheno5 and Teno5, which are actually shown as secondary shock structures, which were shown in the first figure. A little bit more on shock resolution. It's a little bit easier to see in these graphs, where you have this numerical dissipation by this first order. As you can see, that it really smooths out the problem and really takes down the shock time, as well as where you can see in Teno and Weno that you can actually see that shock capturing ability. And these little ridges right back here are secondary shock structures that are coming from the actual ablation process. It's a little bit easier to see on this graph as well. You have Teno5, which is conserving this maximum gradient a lot better than all these other ones, where you have Weno5, the absolute max gradient comes down just a little bit more. Weno3 is just right around in here, and first order is all the way down in here. So as you can see, it's smoothing out a lot more. So some of the results that I found, I looked at both 1 microsecond and 2 microseconds to compare with previous experimental studies. So the shock location at 1 microsecond was 0.93 millimeters, all the way down to 0.88 with Teno5. These shock position and values agreed with shadowography within about 0.15 millimeters, which was found to be an okay amount in previous studies. As well as you can see numerically in these shock gradients is that the Teno5 preserves the highest shock gradient, where the first order upwinding actually does not preserve the shocks as well. And then again, at location of 2 milliseconds, or microseconds, excuse me, you can see it goes from 1.37 millimeters all the way down to 1.27 millimeters. This is within about 0.3 of shadowgraphy experiments at 2 microseconds. But again, it was also shown in previous studies that this is about an okay amount to be at, and still that it preserves shocks, or these higher order methods do preserve shocks a lot better than this lower order method. So a lot of these higher order schemes improve the accuracy and resolution, even with modest computational costs. The jump between 6 milliseconds and 12 milliseconds per runtime seems like a lot, especially when you're looking at over a couple hour basis. But especially if you're trying to get those shock capturing methods, when you're looking at Weno3 and Weno5, that 5 millisecond difference is little to none. But even though this Teno5 is really high, it does lead to longer run times, but you still do get those better shock capturing methods. So kind of what to expect is the simulation captures a lot of primary shock propagation, secondary shock formation, and I'll show you that in this animation in just a second, and this plume ambient gas interaction. And a lot of the things that we see is that the higher order reconstruction enables accurate resolution of transient shock structures in these laser-driven flows, and as well as that these numerical choice methods actually do impact like what this predictive CFD capability has. So you can kind of see it coming out in a very circular method. Again, it's kind of hard to see in this lighting, those secondary structures coming out, but especially in this really small part, there's little ridges that come up right here that actually show those secondary shock structures that have been seen in numerical experiments. So I'd like to acknowledge the Leslie A. Rose Department of Mechanical Engineering for helping me out with everything, as well as Dr. Shabazi. That got me really into a lot of the CFD experiments, as well as Dr. DeWalker and Dr. Dick for helping me out with all of my studies. And are there any questions?
So for your simulations, what was your convergence criteria? What did you look at and go, okay, this is accurate, we're converged?
Yeah, so I did a grid convergence study for the accuracy verification, just to make sure that in the spatial resolution that those schemes were coming down and converging in a correct rate. So what I did was a simple advection problem of a smooth curve. So I just had a density curve. You can do the advection problem. And so with that advection problem, especially a simple one, you can find the location as well as basically it has a solution. It's like a it's a partial differential equation that has a solution at every single time and space. So what I did was I compared at each simulation time, and then as well as each spatial grid to that error of convergence. So basically, if I saw that as it was converging, if it was creating that linear, especially like the L2 error was converging at the correct rate, then that was the like it was sent to be good. That's how a lot of these studies, especially when looking at these kinds of materials, or I guess sorry, not materials, but spatial schemes. A lot of the studies do that, and as long as it's converging at a correct rate, it's said to be good.
Can you elaborate on the discretization? How means why you have taken first order, then fourth or fifth order? Why not 2 and 3? And what is the basis function in that?
Yeah, so I looked at first order as kind of a base, since I'm comparing more at these higher order methods. So trying to look at like kind of going forward. So the reason I didn't do like second or third or fourth order, especially for linear methods, a lot of those methods are unstable, and create Gibbs phenomena, especially around really strong shock methods. There are some methods that you can use, especially implicit methods. That are more the second and fourth order. But I specifically chose 3 and 5 because those methods are inherently of odd order accuracy. There's a lot of fun math behind it. But those different methods are inherently third and fifth order. You can go with Tino all the way up to 13, I believe, and with Wino up to 11. And so I kind of made those choices based on not wanting to see a lot of oscillations around those constant discontinuities, which really add into the error. I guess, does that answer your question?
Is there any also like suppose your model could predict her plasma conditions at -6
Yeah, I think as long as you use it with shadowgraphy and trying to get that initial condition correct, I believe it could do that. So I only showed pressure curves, but the solver can actually look at the momentum, energy, and then it can back solve the temperature out of every single save step as well. And so kind of looking at it as well, I saw a very good momentum where you like I had like negative Y values at the wall boundary showing that it's actually pushing pressure onto that wall. Awesome.
Thank you.
Yeah, thank you.
Yeah.